Hi guys, so this is the review of exam 2 material. So I'm going to go through and talk about the things that you should find on the next exam, and then there's a little quiz that you can take as well on Canvas. All of this in preparation for the exam coming up on Thursday. Okay, so let's work through each of these, right? Let's look at, first of all, KNO3. Potassium nitrate. Group 1 metals are always soluble, and nitrates are always soluble. So this has got the double whammy, and so this is aqueous, right? Ammonium chloride. If you remember, the exceptions, right, were to anything being insoluble were group 1 metal cations and the ammonium ion. And so this is the ammonium ion, and so this one is aqueous. Okay, and then we come to sodium sulfate. Okay, so this Na2SO4, again, group 1, always soluble, don't even need to go any further, it's aqueous, right? And then we get to D, lead chloride, and we look at the halides. Chlorides, bromides, and iodides are soluble, with the exception of silver, mercury 1, and lead, and so lead is an exception, so it's insoluble. Okay. Moving on, we go to calcium carbonate, right, and we find that carbonates are generally insoluble. And then it says the exceptions of these are group 1 metals and the ammonium ion. Not an exception here, and so it's insoluble. Chromium nitrate, again going back to this rule of acetates, bicarbonates, nitrates, and chlorates are all soluble with no exceptions. So this one's aqueous, right? And then FePO4, or iron phosphate, again, going down to the insolubles, carbonates, chromates, phosphates, and sulfides are insoluble except group 1 cations and the ammonium ion, and this is not one of those. Iron is not one of those, so it is insoluble. Finally, we go to the sulfates, right? And sulfates are generally soluble with the exception of silver, barium, calcium, mercury 1, lead, and strontium. Cobalt is not one of those, and so this would be aqueous. Okay, so recognizing that the subscripts didn't come through correctly, this question is asking you to assign oxidation numbers to the bolded elements. So O2 would have an oxidation number of 0 because all elements in their natural form have oxidation numbers of 0. Iron, Fe2O3, and so we start with what we know. We know that oxygen's a -2, that gives me a -6. I need a +6. There are 2 of them, so that's a +3. So iron is a +3. Calcium, the chloride ion is always a -1, so that's a -2, so calcium's a +2. Okay. And then nitrate, the nitrogen in nitrate, again, -2 for oxygen, -6, got to leave that -1, and so this is going to be a +5, so nitrogen's a +5 in this case. Okay, so let's start by writing the molecular. It's FeBr2. We know that that's aqueous, plus Na2CO3. We know that that's aqueous. And now we're going to swap. On the other side, we have FeCO3. And then we've got 2 NABR. Sorry that went off there, but we know that NABR is aqueous because it's the sodium and chlorides, bromides, iodides are soluble and not sodium is not an exception. And then we go to the carbonates, and carbonates are insoluble, and so this is a solid, right? So now if we go to the total ionic, we know that this is Fe2 plus 2Br minus plus 2Na plus CO3 2 minus, and that goes to FeCO3, can't break that down because it's a solid, plus 2Na plus 2Br minus. And then the net becomes the Br minus is out of here, the Na plus is out of here, and finally the net ionic becomes Fe2 plus CO3 2 minus, and that goes to FeCO3 as a solid. All right, let's look at this one, and we can take the H2SO4 and combine it with 2KOH to get K2SO4 and H2O, and then that's as a liquid. These are all aqueous. Right, and then this is also a 2 in front of the H2O, right? So the ionics, we can break down everything that's aqueous. We can't break down anything that's not. So I get 2H plus SO4, 2 minus, plus 2K plus 2OH minus, goes to form 2K plus SO4 2 minus plus 2H2O as a liquid, and that doesn't get broken down because it was not aqueous, and so our net is 2H plus, right, plus 2OH minus, and that goes to 2H2O as a liquid. All right, our SO4s, both sides, K pluses, both sides. That's how we get to that net. Okay, so again, this doesn't always come through correctly, but that's a goes to sign, right? That's the arrow. And so for every 2 N2O5s, you get 4 NO2s and 1 O2. So if we have 6.8 moles of N2O5, it says how many moles of NO2 will form, right, if it reacts completely. Well, I know that for every 2 moles of N2O5, right, I get 4 moles of NO2, right? And so multiplying 6.8 by 2, I get 13.6 moles of NO2. Okay, so we want to start off by balancing this. We notice the 2 over here in Fe2O3, and so we put a 2 in front of the Fe on the right-hand side. Now we've got that balanced. We notice the 2 on the Al on this side. We put a 2 in front of Al on the reactant side. And then we look at the oxygens, and I got 3 on the left, I got 3 on the right. That's balanced. Okay, now it says find the limiting reactant. If you've got 1.50 moles of Fe2O3 reacting with 2.5 moles of aluminum. Well, we're going to look at the iron, so 1.5 moles of Fe2O3, and for every 2 moles of Fe, it takes 1 mole of Fe2O3, and so this ends up being 3 moles of Fe from the Fe2O3. Now we'll go through the aluminum, so 2.5 moles of aluminum, and for every 2 moles of aluminum, it produces 2 moles of Fe, and so it stays the same at 2.5. And so the limiting reactant is actually the aluminum in this case, right? Because 2.5 is all that can be produced, and so aluminum 2.5 moles is the limiting reactant. And so it says compute the theoretical yield of Fe in moles. Well, the theoretical yield is as much as we can produce, and therefore it's 2.5 moles of Fe. Okay, so we want to find the molarity. Molarity is moles per liter. I looked up the molar mass at 39.997 grams per mole, and so I'm going to take 5.00 grams of sodium hydroxide divided by 39.997 grams per mole. That turns out to be 0.125 moles. If I take then the 0.125 moles and divide that by the total volume of 0.725 liters, that's going to give me the molarity, and the molarity is 0.172 molar NaOH. So I want to find out how much KNO3 do I need in grams to prepare this solution. So I take 2 liters times 0.1 molar. That gives me 0.200 moles of KNO3. And then I take KNO3 times the molar mass. So 0.2 times the molar mass of 101.103 gives me 20.22 grams. So that's what I would need of the KNO3 to create this solution as required. And what's a good review without an M1, V1, M2, V2 problem? So what's the molarity of hydrochloric acid solution prepared by adding 25 milliliters of, so that's 0.025 liters of 12 molar, or 12 moles per liter is going to give me moles, right? And then we want to know the molarity, so that's M2, and the new volume is 0.750 liters, right? So divide both sides by 0.750. So dividing by 0.750, that's going to give me 0.400 molar. So the first thing to do is balance this, put a 3 here. Now the carbons are balanced. Look at the hydrogens, put a 4 here. Now the hydrogens are balanced. Then take a look at the oxygens, 6 from the CO2 and 4 from the water. That gives me a total of 10. Put a 5 here. And now that thing is balanced. So now that it's balanced, I need to find the number of moles here, and so it's 340 divided by 44.1, and that gives me 7.71 moles. And then I can take 7.71 moles of C3H8 and apply the mole ratio of 3 moles of CO2 to 1 mole of C3H8, right? And then 44.01 is the molar mass of CO2. So now I'm back to grams. So multiplying everything through, you get 1017.95 grams. But if you consider there are only 2 sig figs here, then even this has more than 2 sig figs because of the trap 0. So what you really need is 1.0 times 10 to the minus 3 grams of CO2. Okay, so here we are with this reaction, aluminum plus chlorine going to aluminum chloride, and we're asked to find the limiting reactant. So first what I did was I took the 8 grams of aluminum and I got 0.297 moles of aluminum, right? And then I used the conversion factor 2 to 2 to get 0.297 moles of AlCl3. And then down here, I did the same with the amount of chlorine. Turns out the 0.329 is larger, and so the 8 grams of aluminum is the limiting reactant. Okay, so now we have to look at what is the theoretical yield. All right. So the theoretical yield, we're going to take the 0.297 moles of aluminum chloride. We're going to multiply by the molar mass of 133.34 grams per mole. And we're going to end up with 39.60 grams of yield, right? So that's the theoretical yield, and that would be 100% yield, right? So now what we want to take a look at is we want to look at what is the actual over the theoretical to get to a percent yield. All right, so there's that 39.60. So now if I take 39.60 and that's the theoretical, I put the 17.2, which is the actual, over the theoretical and multiply by 100, I'm going to get 43.4% yield, right? So again, it's important to recognize what we're working with here. This is the actual, right? This is the theoretical. Theoretical comes from finding out the limiting reactant, and actual must be given somehow. Okay, so in this problem, this is our final one in this review, we've got a concentration of 0.2 molar, and we got 50 milliliters of it, so 0.050 liters times 0.200 molar gives me 0.01 moles of this Na2SO4, reacting with an excess of BaCl2, so we don't worry about the BaCl2. And then it says how many grams of precipitate. Well, if you consider the solubility rules, sulfates, right? Barium sulfate is insoluble, so it's a solid. So now we have to go from this 0.01 moles of Na2SO4, and it's a 1-to-1 mole ratio of BaSO4 to Na2SO4, and that then gets me to 0.01 0.0100 actually moles of BaSO4, and then I'll just multiply by the molar mass. And multiplying by 233.38 grams per mole, we get 2.33 grams of BaSO4. And there is our review for exam number 2.